Greetings, fellow mathematicians. We're going to solve this second order ODE using the method of Laplace transforms, and we're going to mention some nice tips to make some of the work a little bit easier. Now, notice in the differential equation, there's no y prime or first derivative term, so we only need the following Laplace transforms: the Laplace transform of y, the Laplace transform of the second derivative, and the Laplace transform of the right-hand side, the exponential function. Now, it's worth pointing out, in your standard Laplace transform table, it's usually expressed where t is the independent variable. But in my differential equations course, I usually like to use x as the independent variable. So just make sure you're comfortable with whatever independent variable you're using in your course. It might be stated in terms of t here, but you might be using it in the differential equation where x is the independent variable. Really, it doesn't matter. Now, to get started, we're going to take the Laplace transform of each of the three terms, and we can do that because the Laplace transform is linear. So step one, we'll take the transform of each term, take the transform of the second derivative. When we take the transform of the 4y term, we can pull the 4 out front, since the Laplace transform is linear. And first tip to mention, even for my best students, they sometimes forget that they're taking the Laplace transform of the right-hand side. So worth emphasizing that, take the Laplace transform of both sides. So we'll take the transform of e to the negative x. And again, depending on your course, you might be using that here and seeing it instead as e to the negative t, using t as your independent variable instead of x. All right? At this point, when you calculate these Laplace transforms, never use the improper integral definition that you were first introduced to. Always use your Laplace transform table to calculate these transformations. So let's take it one at a time. We have our transform of the second derivative. That is this transformation right here. And that's where we're going to use the initial conditions. So if we write it down, we get s squared times f of s. We have minus s times the function initial condition, which is 1. And then minus the derivative initial condition, which is 0. And the other term here, the Laplace transform of y, or your Laplace transform of little f, that's just capital F of s. So we get 4 times f of s. And again, don't forget to take the transform of your right-hand side, and that's where we're going to be using a, whatever is multiplying the independent variable up in that exponential. That's going to be noticed to be -1 here. So in that transformation, we're going to be using a as -1, and if you plug that in here, your transform will be s minus -1 in the denominator. So your denominator really becomes s plus 1. So we get that transformation on the right-hand side, 1 over s plus 1. From here, we're going to want to solve this for f of s. Let's clean this up a little bit. So first off, notice I don't need the -0, I don't need the times 1, and my two f of s terms, I can factor f of s out and get in parentheses s squared plus 4. All right, I have the minus s by itself. That equals 1 over s plus 1. We're right on the verge of mentioning another useful tip, but let's go ahead and first add s to the other side. So we're going to keep the left side basically the same, but I'm going to add s. And this is where I want to pause to mention what could be a useful tip. Some problems you'll want to do this, maybe some problems you don't, but worth mentioning either way. Now, in a previous problem, I mentioned maybe you want to combine separate fractions into a single one. Here, the tip that I want to mention is I'm going to advocate we're going to keep these separate. We're not going to combine them together. That's because when I divide by s squared plus 4, that's to solve for f of s, I'm going to get s divided by s squared plus 4. And if we take a look at that, in a transformation pair, that's going to match back exactly in the f of t column. That's going to match back exactly to cosine. That's b squared in the denominator. That's going to match back exactly to cosine of 2t. So the tip here is recognizing that if I were to go ahead and divide the s divided by s squared plus 4 term, that already matches a known Laplace transform pair. And that's going to save you a little bit of work in doing the partial fraction decomposition. So to clearly state it, the tip that we're going to be using here is for this one, we're going to keep the fractions separate. Sometimes you want to combine them together. Here, we're going to have a simpler partial fraction decomposition if we keep these separate. Now, we still need to divide the 1 over s plus 1 by s squared plus 4, but that'll just give us an extra factor in the denominator. So let's go ahead and follow that tip. I'm going to divide by s squared plus 4, and that's going to be so I can solve for f of s. So we get f of s here. Divide your s term by s squared plus 4. But don't forget to divide the other fraction by that. So we'll get factors of s plus 1 times s squared plus 4 in the denominator, and that's over 1. So up to this point, that is a good amount of work through the problem. This is your solution to the differential equation, but it's the solution in the frequency domain. We're going to rewrite this so that way we can transform back using existing Laplace transform pairs. So let's go ahead and get to the partial fraction decomposition. The tip that we mentioned a few moments ago of keeping those two fractions separate will lead to a simpler partial fraction decomposition just for that second fraction. If you were to combine both of these together to a single fraction, you would end up with more work for the partial fraction decomposition. This tip is only beneficial because that first fraction exactly matches an existing Laplace transform pair. So let's focus our attention on doing the partial fraction decomposition for that second fraction. All right, this denominator contains both types of factors. We have a linear factor, s plus 1, and then an irreducible or unfactorable quadratic factor, s squared plus 4. Your partial fractions come out to a over s plus 1, and then bs plus c divided by s squared plus 4. We have three unknowns, a, b, and c to solve for, which means we need three equations. We're going to arrive at those three equations by first eliminating fractions completely from here. So let's multiply both sides by that LCD. Multiplying that LCD to the first term, the s plus 1 factor cancels, leaving you with a times s squared plus 4. Multiply that LCD here. The s squared plus 4 factor cancels, leaving you with bs plus c times s plus 1. I always advocate to my students, whenever you have irreducible quadratic factors, to not plug in values for s to solve for a, b, and c, but to instead go through the method of equating coefficients. So we're going to multiply out this whole right-hand side collect your like terms, powers of s's together, and then equate the coefficients of s equal to one another on each side. Worth pointing out, on the left side, there are no powers of s, but you can think of them as being there with 0 coefficients. We'll get to that in a moment. So first, let's just go through all the algebra for the right-hand side. Just distributing and multiplying out, we'll get as squared plus 4a. And then FOIL or expand this term, looks like we'll get bs squared plus bs, and then plus cs plus c. We're going to collect like terms together, first for s squareds, and it looks like we have a and b. So we can think of factoring out s squared. All right, we should have some s terms, bs and cs here. So factor out s and get a coefficient of b plus c. And we should have constant terms left for a and c. All right, now that's the work for writing out the right-hand side to equate coefficients of s on each side. Let me write this left side as 0s squared plus 0s plus 1. And now we can equate coefficients a little bit easier here. We're going to get 3 equations. We're going to get an s squared equation, an s equation, and then a constant equation. And if we do that, coefficient of s squared on the left is 0, but on the right, your coefficient is a plus b. All right, that's one of 3 equations that we're going to need. Next, we'll equate coefficients of s. 0 should equal b plus c. And your last equation, coming from equating the constants, you'll get is 1. That equals 4a plus c. And we now have our 3 equations for the 3 unknowns. Now this could be a little bit complicated in general to solve, but this one is actually pretty easy. The first equation, we can solve it to get b equals negative a. I can take that and plug it into the second equation. That's going to give me negative a plus c equals 0, which we can rewrite to give c equals a. And I can take that and plug it into the last equation. And it looks like if we plug that in, c as a, we get 4a plus a, which would be 5a. We get a simple equation here, 1 equals 5a. And we can easily solve that for a, divide by 5, to get a as 1 over 5. And from the work above for your previous 2 equations, you can just plug that back in. Having a as 1 over 5, we get c as 1 over 5. And plugging back in a to the first equation, we get b as negative 1 over 5. And now we have our values for the 3 coefficients, a, b, and c. We just need to plug these values back in here and then account for the full f of s. We're going to get to that right now. Now that we have our values for a, b, and c, we just need to plug them back in and then rewrite our f of s so that way we can do the inverse transformation. So let's just go ahead and first recognize we have this first fraction, which we did not include in our partial fraction decomposition. I'm just going to write that down immediately. And now we're just going to plug in the values for a, b, and c that we found. Since a, b, and c are all fractions, I'm just going to pull them out front. This term, I'm going to split that into two fractions, bs over the denominator, and then c over that denominator. So let's plug in a as 1/5. We're going to plug in b as negative 1/5, but I'm going to pull that out front and split that into two fractions. So it looks like we can write this as minus 1/5 times s over s squared plus 4. And then we also split this and get another fraction with c in the numerator, but c is 1/5, so I'll pull that out front. All right, and what we're going to recognize is we can actually combine two terms together here, the first and the third. We have a coefficient of 1, a coefficient of negative 1/5. Add or subtract them together, and it looks like you would get 4/5. So that'll be 4/5 times s divided by s squared plus 4. This we're going to leave alone, since that matches an existing transformation pair. But this last one, while it closely matches your sine transformation pair, we have b squared in the denominator, but we're missing a factor of b. So if b squared is 4, that means b is 2. I'm going to want to multiply and divide by 2. So let me basically multiply by 2 here, and then divide by 2. The 2 in the numerator, I'll move into the top. The 2 in the denominator, I'll just multiply that to 1/5. So we'll write this as 1/10. That's your 1/5 times 2 divided by s squared plus 4. And all three of your terms here should now match exactly transformation pairs in your Laplace transform table. So all your factors are properly accounted for. We just need to go backwards here. This is your f of s. And now we can do the inverse transformation back to our solution, y as either a function of t or y as a function of x, depending on whatever independent variable you're using in your course. So if we do our inverse transformation, I'm going to write it down first with x that I use in my course. This fraction, s over s squared plus 4, that's going to transform back where we're using b as 2. That transforms back to 4/5 times cosine of, instead of 2t, I'm going to write it as 2x. The middle term here, that's going to match your exponential transformation pair, where a is negative 1. So that will transform back as 1/5 times e to the negative x. And then your last fraction here, that matches your sine transformation, where we're using, again, b as 2. So it looks like that transforms back as 1/10 times sine of 2x. And that is our solution to that differential equation by using Laplace transforms. Now, again, I use x as the independent variable in my course, just so you can write it down, so that way you get it in terms of t, which you might be using in your course. Your solution would look like the following: 4/5 times cosine of 2t plus 1/5 times e to the negative t, and then plus 1/10 times sine of 2t. These are both the same solution, just with a different independent variable. I use x in my course. You might be using t in your course. Hope you enjoyed this video of going through Laplace transforms. I hope you're learning a lot. If you are, leave me a comment below. And always support the channel, like and subscribe.